ensign exam, which will be 1 week from today, the seating arrangement is as for quiz 2, so which means all the MSPC scholars will be in MSP 356, while all MTech students will be in MSP 355. I hope this is what we follow. So we have whatever may be the official announcement, what it is I haven't seen, it's probably the same as what it was in the earlier quizzes, but this will be the seating arrangement for CH50, this course, this DVD seating arrangement. The courses will be a full course, but focus will be heavily on mixtures, which is what we have covered since the second quiz. Of course, we already started the mixtures in the first quiz, but whatever probably a good clue is whatever was left out of pure components in quiz 1 and 2 might also appeal. So the portions is comprehensive. Are there any questions on the answer? So it will be, in terms of difficulty, of course, what I say might not actually, you might not agree with it. It will be more along the lines of quiz 2 and rather than quiz 1. That's what I'm expecting to say, but it might turn out otherwise. It might turn out to be easier than quiz 2 or more difficult than quiz 1. So I cannot say. But I try to set it along the same lines as quiz 2. It will be a mixture of both numerical and analytical. So you should be prepared for both. So that's what I have to say on the ends. So we will now wrap up this course. Even though the courses that I will be covering today are not strictly included in terms of big problems in the ends, and I think it's useful to know this as something beyond the course outline. Right? So for those of you who are interested in learning beyond, and which I haven't been able to cover for lack of time. If we had time, I would have covered more on these topics and included them in the course. Since we don't have enough time to cover, we'll just briefly look at it. We're looking at the combined phase and reaction equilibrium. We'll just wrap it up quickly. The example that we were studying was what we have the ammonia reaction taking place in the gas phase. And on top of it, we also have water, ammonia absorbing in the liquid phase. So ammonia, nitrogen and hydrogen reaction will be entirely in the gas phase. So this is somewhat a complementary example we saw earlier. The production of carbon black is a very common example discussed in many books. The reaction itself is taking place in two phases, which means that some of the components in the reaction are in one phase and some in another. There we really have to invoke any phase equilibrium criteria, because carbon is the only substance in the solid phase, and the gas phase components are not present in the solid phase. So we do that. But here it is complicated by the fact that though the reaction is taking place in the gas phase is in equilibrium with the liquid, and ammonia is present in both phases. So if you consider more complicated cases, as considered by Stanford, both nitrogen and hydrogen are also absorbing. Water is also present in the gas phase. That will be very complicated, but this is the minimum that I can add to the reaction equilibrium ammonia case that we should consider. So on top of the reaction that takes place, that of ammonia, which would lead to the following criteria for chemical equilibrium. And here both all the components here are in gas phase, but it doesn't really matter for ammonia, which is present in both phases, because the chemical potential of ammonia in the gas phase is equal to that of itself in the liquid phase. So we have this additional equation which we didn't have in the purely reaction equilibrium that we consider. So this is clearly an example of a combined reaction and phase equilibrium. We have applied the degrees of freedom, and I pointed out that the degrees of freedom in the phase group will deal with mole fractions, but if I have to actually solve this problem, I have to express the mole fraction in terms of the mole numbers or the mole ratio. Right? So those variables come into the play, and the actual phase group, the degrees of freedom, I mean the number of variables will change, right? The equations will remain the same as in the consideration of the phase. So if you look at this, if you focus on the problem which had reaction alone, if I just forget this, if you recall, we had the temperature, pressure, and then we had alpha, beta. It was a ratio, initial ratio of, I think this was NH2 naught by NN2 naught, and this was NH3 naught by NN2 naught. So because the equation was this, and the chemical potentials are dependent on the temperature, pressure, and the composition of the mixture, which here were two composition variables, either hydrogen and ammonia or nitrogen, ammonia, water, right? So those were the variables, but we saw that in the actual reaction equilibrium problem, these mole fractions had to be expressed in terms of the mole numbers, which would involve the initial mole numbers, right? These come as parameters automatically into the equations. And the other one was x and 2. So 5 variables. So we fixed the temperature, pressure, alpha, beta, and then we go to find this one equation only we have. Now, all of these variables remain as they are in this combined problem. But you will see now that there will be an additional variable. If you write out the material, for instance, if I want to write here NH3, because there if you saw all the mole fractions would involve the mole fractions in the gas phase. But if you look at this, if I want to write, for instance, XNH3, right? XNH3 would be NNH3 by NNH3 liquid by NNH3 liquid plus NH2O liquid, which will really remain, it is not going to change at all. So if you now start expressing the compositions in terms of the, I will leave it as an exercise for those of you who are interested, you will find that now I have these variables, but I have two equations. Obviously there will be another variable that will come in, and you can easily choose one of the two, because now the ammonia, if I write the balance for ammonia, is formed out of the reaction, but ammonia is distributed between the two phases. So you will see that the second variable would be NNH3. Either you will take it to be the gas phase mole number or the liquid phase by NN2 naught. You will see that you cannot avoid this variable coming into the equations when you try to express the mole fractions of the different components in terms of the initial mole numbers and the conversion, right? So that will be the additional variable, and I have two equations. So if I specify, I continue to specify these four, right? And then this will be the two variables that you would have to determine from the two equations. So the problem is exactly solvable. There are as many variables as there are equations. So this goes on a case-by-case basis. You can clearly see in this case that 6 variables are there and 2 equations. So you know that there are 4 degrees of freedom. If you strictly apply the phase rule, C minus pi plus 2 minus r, you do not get that. Because now what has happened is we have actually introduced new variables to express the mole fractions in order to solve the problem. This seems unavoidable in any problem involving reaction equilibrium. Right? This is as much I have to say. So the problem in setting up reaction phase equilibrium is one of the material balances and the chemical equilibrium and the phase equilibrium equations. Right? So that is the basic problem. It involves a little bit more of thought to express this in a very general framework. So I have not attempted to do that. Now we will skip this. So we are moving away from reaction and phase equilibrium. I want to discuss certain aspects of the vapor-liquid equilibrium itself that we discussed. Right? And I want to point out the connection between the Henry's law and the Raoult's law. So this is often a source of confusion. Right? And in this context, Stanley, for instance, also talks about what is called as a non-simple mixture. Now, what is a non-simple mixture. I'll explain that briefly. Now, all of these are connected, so I'm going to tell you how they are connected and what is the relevance to these topics we've already introduced in one way or the other. What he means by non-simple mixture is the following. Now, if you take the ideal solution definition of ideal solution is FIIS, that is the fugacity of every component in an ideal solution, is Xi, that is the mole fraction of that component in the mixture, times the pure component fugacity. Now, this is totally unambiguous. However, if you see, some books also say that it is Xi times the fugacity of the component I at the same temperature, pressure and phase of the mixture. Now that is somewhat contradictory, because for a pure component, once you specify temperature and pressure, the phase is automatically specified. It can be in two phases, liquid and vapor, in which case both the fugacities would be the same, right? So if you leave it like this, there is no problem. But however, the problem apparently comes in the practical calculation, and I indicate that is what leads to the concept of a non-simple mixture. So, if for instance I look at the typical vapor liquid equilibrium, let's say P, temperature is fixed, P is fixed temperature X or Y of one of the components, binary mixture, let's say. Typical vapor liquid equilibrium. So, this is the component A. So, this is the boiling point of A. Right? And this is the boiling point of B. Now you take a particular mixture, vapor liquid mixture. This is clearly the vapor and this is the liquid. Now you see that at this temperature, which lies between the boiling temperature, pure A and B at this pressure, at this temperature, what would pure B be? Would it be a liquid or a vapor? Forget about the mixture. At this temperature, B would be liquid or vapor? It would be liquid, obviously, because the entire thing is a liquid region. So clearly this falls. This point is what I am talking about. What is the phase of this point I am asking? It is clearly liquid, right? Now on the other hand, if you look at component A, right? Component A, consider this liquid mixture now. Now I am moving from here to here. Consider this liquid mixture. Now both A and B are liquid. Right? However, at this temperature, A is actually a vapor because it is already boiled. So at this temperature, it is the vapor in it. It will be vapor. This is where there seems to be a problem in interpreting. Now, if I apply the modified Raoult's law, so let's assume ideal gas mixture. We are not talking about the vapor phase here. Now, we are going to excite Fi. What standard indicates that it is strictly FIL TP and not simply FI TP. So then he introduces the idea of a fictitious liquid for the fugacity if A were a liquid at that temperature and pressure. So it's somewhat a hypothetical substance again, right? So it's not doesn't really have an existence because at this temperature clearly A is in the pure A is a vapor. So if I just leave it like this, it is the ideal solution. For A, this would mean that this is there seems to be a contradiction because actually A, I am trying to describe the liquid fugacity of A in the liquid phase, but I am actually calculating the pure component fugacity, which is actually a gas actually. So this leads to some problem in the actual calculation. But what he points out that even though I should write it in a hypothetical way, he says this difference in temperature is not too much. It is still a good approximation to approximate it as. Otherwise, you have to use some extrapolation procedure, which seem to be purely empirical, to estimate that fugacity. So what he example where you cannot replace the liquid fugacity, the fugacity of the component in the liquid phase, right, by the saturation pressure comes in absorption, which is why you go to Henry's law and not to Raoult's law. Right? So let us now consider the same, because absorption is also basically gas liquid. Right? Two components I can say, both are in the gas phase and both are in the liquid phase. This is a very general problem. Right? So what he says though, typically in absorption, the temperature, the component which is absorbing, let's say oxygen, he gives an example, oxygen in water, and we want to study absorption of oxygen in water. Right? Typically, the component that is absorbing, its critical temperature, Tc1, let's call it this component 1, Tc1, the critical temperature of that component is often much greater than the actual mixture temperature. Right, so what this means is that the actual mixture temperature is in liquid phase, but it can never be as a pure component, it can never be in a liquid, it will always be a vapor. So the point here is that in that case, what he says, well, we are considering absorption of oxygen in water, and in general this can also contain some, this is a binary, it looks like vapor liquid equilibrium only, but why we cannot use the Raoult's law in this case for A, that is the question. For instance, we can still write E, Y, O, 2, but we cannot write, this would be an analog of that expression, but it's simply not practical, or numerically it is not an accurate model. So if you take a look at Raoult, who gives ammonia absorption in water, for instance, you take a look at that very famous figure which we have actually pointed out earlier. He gives the actual absorption characteristics of ammonia in terms of partial pressure versus mole fraction, and then you will see two dotted lines, one which represents Henry's law and one which represents Raoult's law, and he shows how the Raoult's law is totally off even at very low solubilities. Right? So the problem here is that while here I can approximate it as, take it as liquid, because the temperature difference is typically in vapor liquid equilibrium, where especially Raoult's law is applied, or even modified Raoult's, so it's not much. So we can effectively, even though the component is actually a vapor in the pure phase, this approximation holds. But in the case of gas absorption, typically the temperature of the mixture is actually such that the component oxygen can never be even closely, remotely closely a liquid. It will be always be a vapor or a gas only. So in that case, the Raoult's law approximation fails, and so what we have to effectively, one way of doing it is to use the Henry's law. So I can say that this is equal to xO2. Now this becomes purely empirical because there is no meaning to the Henry's law constant, right? So, fundamentally, what is the Henry's law constant or the Henry's constant? What does it depend on? How is it related to the fugacity? Right? So, the point, the relation between the Henry's law and the Raoult's law, they are two opposite poles. If you look at them in terms of Henry's law versus Raoult's law. However, it is possible to establish a connection between the Henry's law on the one hand and the Raoult's law on the other hand if you consider the modified Raoult's law and what I am going to call as a generalized Henry's law. Right? So the modified, so what we are really focusing on is the fugacity of a component in the liquid phase. Component I, right? Now we know that I can write it, for instance, as xi, hi of write it like that, but we know that Henry's law is valid only for dilute solutions. So what is typically done is to introduce an activity coefficient. It is called as the Henry's activity coefficient that will generalize the Henry's law and make it applicable to higher solubilities also, right? So that this may be regarded as effectively a definition of the activity coefficient with respect to Henry's law. Now, if I move to modified Raoult's law, I can go back to the earlier discussion where the modified Raoult's law, if I apply, right, then I get Xi, and here typically rather than just leaving it as a phi of Tp, you introduce the fictitious liquid phase fugacity, right, times the regular gamma I. So this sort of gives a relationship between the Henry's law and both are equivalent, right? But then if you consider it in terms of the generalized Henry's law, so now what does this give for the activity? What does this mean for this? Does this give a definition of anything, right? So we'll see that by seeing that in the limit as Xi goes to 0, we recover the Henry's law. In the limit, if I take Xi goes to 0, I will get this to be Xi Hi of Tp. Right? Xi Hi of Tp. This will become, what does this become in the limit of so this will become Xi FIL of Tp times gamma I infinity, because we have seen introduced two different limits of the gamma. Gamma 1 for x1 goes to 1 will become 1. We haven't quite looked at how gamma 1 would be for x1. It is the same thing we saw for the partial molar property. The gamma is very much like a partial molar property. We saw that in the limit of the mole fraction of a component going to 1, the partial molar property of that component in the mixture will go to the pure component property. But in the limit as a mole fraction of that component goes to 0, we get what is called as a partial molar property at infinite dilution of that component. That is the other limit, right? And so we now see that I have to introduce the gamma I norm. And so now by cancelling the two, I now actually get an expression for Hi of Tp. That is, we now get a fundamental definition or approach to the Henry's law concept, because at this stage it remains purely empirical. This is something that I am introducing to make it match with the experimental value. But by considering the generalized Henry's law and the generalized Raoult's law, what we are effectively saying is that the coefficient Hi is actually given by the fugacity in the liquid phase of the component times gamma I infinity. Now, so I can now replace this. So I can write this as Xi. So by considering it in the limit, I get an expression. So I get this is FIL of Tp times gamma I infinity. Now if I compare these two, again I have gamma I H also. Right? So this is, sorry, again. Let's rewrite it again. So now I've got, this is one important relation, because it gives relates Henry's law constant to the fugacity, which we know, right? Now here, if I now look at it now I want to see how are these two gammas related, for instance. So to do that, I consider these two, right? And simply cancel xi again. So I get hi of Tp gamma ih is equal to FIL of Tp gamma I. This is what I get, right? There are two different ways of writing the fugacity. And now here I will replace hi Tp by FIL of Tp times gamma I infinity. And so then what do I get? So I cancel FIL of Tp and then I get gamma I is equal to gamma I divided by gamma I infinity. So I now also get a relationship between the gamma that we know, which we define effectively through the modified or introduced through the modified Raoult, so how it is related to the gamma appearing in the generalized Henry's law. So this gives the relationship between the two activity coefficients. Now, how does this help us in actual calculations? Now, in actual calculations, certainly when we go to VLE, typically, when we go to VLE, right? So we simply say use the regular gamma A, whatever, depends on Tp and X. And the regular VLE, this seems to be a good approximation. This so-called fictitious liquid fugacity, right, can be approximated as the saturation pressure of that component, which leads to the modified Raoult's law. So what happens if you're considering a case like this? What do we do? Right? So for here, if the Henry's constant is given as a function of temperature and pressure, right, then obviously I will go to this expression, right? But now the original Henry's has value only for low solubility, but to extend it to higher solubility, we have to find gamma IH. But I've just shown that gamma IH is equal to gamma I by gamma I infinity. So any of the activity coefficient models that we have considered can be used to calculate the Henry's law gamma also, right? So to treat the absorption problem, if I have the Henry's law constant, I will do that, and then I will calculate, extrapolate it to higher solubilities by calculating gamma I from an activity coefficient model. We know how to calculate gamma I. Once you know gamma I, you can calculate gamma I infinity, and then you simply get the Henry's law gamma I. So I can treat an absorption problem. However, if that is not given, suppose that's not given, then I have to fall back on this, and here the FIL, so if I'm forced to use this expression, I cannot replace FIL in typical absorption problem, I cannot replace it by Pi sat of T, which is why the Raoult's law will not work for absorption, right? So for that, there are certain extrapolation procedures outlined to calculate the so-called fictitious figure. I will write that expression. It's there in the standard textbooks, and this will just help you to extend your scope of calculations to include absorption in a very general way, rather than just be restricted to the Henry's law alone. So I'll just write those, give you the reference for those correlations. For instance, one correlation that is there in Sandler is the corresponding space correlation of Raoult and share. What this gives you is, it gives you actually the FL, that is a fictitious liquid fugacity. Because now we say that for the absorption we cannot replace it by saturation pressure, then what can we, how do you calculate it? It cannot be calculated as a regular fugacity of that component, because the regular pure common fugacity of component I would correspond to a gas phase fugacity, whereas it is actually in the liquid phase here, and we are interested in the fugacity of the component in the liquid phase. That is one of the explanations given why that will fail. So what this gives is, it gives this fictitious sort of an empirical type formula that relates the fugacity of the any component I. Because this is what I have to calculate. Because gamma I can calculate, I know how to calculate. I have to calculate this now, right? So that is purely done empirically. This is again a fictitious liquid volume, because I know the pure component I is not in the liquid phase. I'm sorry, this should be in reverse, inverted. T makes is greater than PC. Sorry, that should be. This is somewhat like a pointing correction factor, right? So this is the again a fictitious liquid volume has to be assigned to that component, even though it's not. That is why it's fictitious. I put it within brackets, the L, but the actual component is not a liquid. And then what you have is that you have a formulation given graphically as FL. FIL of P equal to 1 bar. This quantity, right? I'm sorry, this quantity is given in terms of a graphical formulation. Now maybe you can also fit it to an analytical formulation like we have made. Divided by PC. That is the critical pressure of the component. It could be any component actually, because this makes it, that's why it is a generalized correlation. What we plot on the x-axis, the reduced temperature, right, versus a reduced fugacity. The fugacity has the same units of pressure. You get a scale to the critical pressure. T equal to 1 bar is what I get from the graph, and it looks something like this. Then, if you look at Sandler, this is maybe I can give you the actual reference. The figure is, I don't have it in the 4th page. Here it is. The figure is 11.1.1 of Sandler, the 4th edition. Given the figure is actually due to crossness and shade, is taken it from that table. So you get this, and then there's a table that gives the VIL, fictitious liquid volumes of the components that you have to use in the formula for various typical gases, which whose solubility we are interested in. So what we do then, given a particular substance, let's say oxygen absorbing, this is all corresponding to the component that is absorbing, right? So I know what its TR is, so I go there and calculate what FIL, TP equal to 1 bar by PC is from this graph, because this graph applies to all substances supposedly. So the correlation has been obtained by correlating the absorption behavior of many gases, right? So then, so I calculate that. So I know the PC of the substance, so I can calculate this. And then I go to the table and whatever substance I want, I will calculate this. Then I will calculate this quantity. Right? So then the gamma I can be calculated using a typical atomic absorption model. But it looks like, if you look at, for instance, the typical Van law and other models, the substances for which the parameters are available may not correspond to what are typically encountered in gas phase, and Sandler uses something called a regular solution theory to calculate the gammas. But anyway, that's another matter. But the point is that if you're using this equation, then gamma is the only thing that you have to calculate theoretically. That can be done using any excess Gibbs free energy model, right? Provided the parameters are available for the particular mixture, right? So this sort of connects the Henry's law on the one hand and the Raoult's law on the other. The connection is not possible at that level, but by introducing a generalized Henry's activity coefficient, we can do this connection. So, are there any questions on this? So, we still have about 10 minutes, and I'll wrap up the course by discussing the limitations of the activity coefficient model that we have considered. So, we looked at typically the one that are commonly used or introduced in textbooks are Vanguard, Mark-Lewis, and then we also have Wilson and NRPL and so on. Now, the problem with these activity coefficient models is that the parameters for a given mixture, what are we going to choose, right? So, the parameters in these models typically require some experimental data. We have seen a dramatic case where we are just using the azeotrope information, we could calculate the parameters of any of these models. We have seen that, right? How to calculate that. Of course, if you have data available over a wider range, then you can use it to do some regression analysis. For example, let's say you have bubble pressure data, right? So then you obviously would use the experimental bubble pressure data. You can do some kind of least squares estimation of the parameters by comparing or minimizing the error between the predicted bubble pressure and the experimentally available pressure. But the point here is that if anyway you require experimental data, you can ask what is the effect of this model. The value of these models is that using limited experimental data, we determine the parameters and then use those parameters to extrapolate to regions where experimental data might not be available or it might not be feasible to conduct. So that is a value, but models still have value in that. But if you want to go to a stage where you can calculate the activity coefficients without using experimental behaving data directly for the substance, then we have to go to higher order models, and I'll just mention one or two of them and describe how they are done. The two models that I discussed is one is the UNIQUAC model and another is the UNIFAC model. So these models, to a large extent, avoid use of experimental data, but they use it indirectly, in the sense that the way the parameters that go into the model, right, have been determined by correlating experimental data for a large number of substances. And so for a particular substance, you don't necessarily need which expert data might not be available at all. You can still use those ideas and calculate the activity coefficient. So let me just briefly explain. Here the excess gets free energy is given in terms of two terms. One is called as the combinatorial excess Gibbs free energy. The other is called as the residual Gibbs free energy. This also would mean that actual gamma I can also be written as in this manner. So how do we calculate these residual contributions and the combinatorial contributions? Now, these are effectively determined by geometrical parameters. These require energetic information. Now, typically the parameters that appear are, I'm just listing one or two. One is Ri, which is a volume parameter for species I, and then Qi, which is the surface area species I. And then we have, so the UNIQUAC has these parameters. You have an energy parameter that is denoted as tau, some kind of energy of interaction. Now, where does this lead us in calculation? The calculation part comes because the Ri is regarded as, here is where what the additional angle to the UNIQUAC model comes in terms of what are known as group contribution methods. What the idea behind the group contribution method is that a molecule is regarded as composing of several functional groups, right? So for example, methanol, you say we have CH3 and OH. If we take ethanol, you still have CH3 and OH, you have CH2. So thousands of molecules can be constructed using a few functional groups. So the main idea behind the group contribution method is that this is given. So I identify, for instance, for methanol I have CH3 and then OH. So the Ri for methanol, for example, could be written as R CH3 plus R OH. So you go and calculate the volume parameter for the functional group CH3 and the volume parameter for the functional group OH. Right? Now if you go to ethanol, you will, on top of it, for ethanol, this is for methanol. For ethanol, it will be RCH3 plus ROH plus RCH2. So these remain the same. So what the basic idea, assumption, is that the functional group behaves in the same way, whether it is in methanol or in ethanol. So I can use the same volume parameter. Now these are tabulated. So rather than tabulate, thousands of molecules, rather than tabulate the volume parameter is really impossible. So what has been done by some kind of fitting still is hidden is there to BLE data you have, and also using the molecular properties of the model. What are those standard available are these volume parameters and surface parameters are available for the various functional groups. So what's handled, for say from 85 functional groups, I can construct thousands of compounds. So we don't need to tabulate the parameters for 1000 compounds, rather for just 100 functional groups, and I can calculate whatever molecule. If I identify the functional groups which are fairly common, especially organic liquids and so on, the same functional groups keep recurring, and so I can calculate these volume parameters. Now the main disadvantage of the UNIQUAC model is that the energy parameter remains an adjustable parameter. For that we need the vapor liquid equilibrium data for the particular mixture. That is how it is to be calculated. So still it doesn't overcome the limitation fully of the van law or the Morgan test. But to a large extent you can calculate a big chunk of the activity coefficient can be calculated purely using the available tables. Of course, how the log gammas are dependent on Ri and Qa, that's another matter. But you depend on the mole fraction and so on. So you have a volume fraction, the surface area fraction and so on, which will bring in the mole fraction of the component in the mixture. And then you have to construct the activity coefficient. Now the UNIFAC model overcomes the limitation of the UNIQUAC model in that the residual component is also calculated using group contribution methods. So there also we associate with each functional group a certain energy, right? And then depending on how many functional groups are there, the formula might not be as straightforward as what I have written here, but you can calculate in principle from the energy values listed for, again these have to be tabulated, just as these are tabulated, the energy parameters appearing in the residual component are also tabulated in terms of the functional group contributions. What would a functional group contribute to the energy parameter, let's say tau ij, right? And then there is a formula that tells you finally how to construct the energy parameter associated with the mixture, right, from these functional groups. So again, these have probably used some BLE data for a limited number of substances, because as I said, because if you have 20 substances, let's say, they might be made up of predominantly 2 or 3. So we don't need the data for each and every of those 20 substances, right? If you have, let's say, out of these, maybe 5 of these substances might have all the functional groups that you need. So you make limited use of experimental data that's already available and calculate the functional group contribution to the energy. So this way we complete the calculation with minimum use of direct experimental data. Already some experimental data has been used to calculate these functional group contributions. But beyond that, let's say you have a new substance for which no experimental data is available, but you are able to see that it is composed of the functional groups for which data is already available. Right? Then you can go and use that as a predictive model. That is why the UNIFAC is, this is sort of a semi-predictive, whereas the UNIFAC, which calculates the residual contribution also from group contribution methods, can be called probably as more of a predictive model, in the sense that if no experimental data is available, then the van log and the markers will give you no clue on how those parameters are to be determined. Whereas here, if you know that the molecule, for instance, the mixture for which we don't have any data at all, but a composed of molecules which can be further decomposed into functional groups for which data is already available, it has been obtained making use of information from those substances for which data is available, and which also includes these functional groups. Right? So you have to know that it's not completely predictive, but some experimental data has been obtained and tabulated in terms of functional groups. Right? Now if we don't have any data on a given mixture, we can go and use those tabulated values, provided the functional group that groups that you have are in those tables. So in that sense it is more predictive than the van log or any of the other models. Are there any questions? So this will sort of be a generalization of a simple algorithm inversion model. Obviously it will require more computational effort, and some of the books even give make available programs on the website which you can use to determine. But the idea or principle behind these are based on more of a molecular or a statistical mechanical approach. It's not a rigorous statistical mechanical, based on some gross ideas from statistical mechanics, which relates the observable thermodynamic properties to the molecular constitution. Some amount of empiricism and some amount of crude modeling is used with some basic background in statistical mechanics to construct these so-called more complicated or complex activity coefficient models. Right? So with that I end this course.